All right, this video lecture is going to cover periodic trends. Before we get into the actual periodic trends, there's a really important concept that you need to understand because we use it to explain the periodic trends, and you will be asked to use this concept in your explanation of the trends. So that concept is Coulombic attraction. Coulombic attraction basically means that opposite charges attract and like charges repel. That's something that you were hopefully taught in like elementary school, but you are not taught the actual name for that concept, which now you need to know. So, when we think of an atom, right, we have positive charges and we have negative charges. So, the positive charges are in the protons, those are located in the nucleus. And the negative charges are located in the electrons, which surround the nucleus. So there is an attraction between the positively charged nucleus and the negatively charged electrons. Amongst the electrons, we talked about this with the flame test notes, there are repulsion forces because like charges repel. So the negative charges on neighboring electrons do repel each other. So we're going to apply this today. There's three trends we're going to talk about. The first one is atomic radius, which is exactly how it sounds. It is literally the radius of an atom, how large an atom is. We measure that from the nucleus, the center of the nucleus, to the outermost electron. Hopefully you were taught that in math. Sounds like a geometry thing. When we look at the periodic table, as we move from the right side of the periodic table to the left side, we increase atomic radius. So elements towards the left side of the periodic table have a larger atomic radius than those on the right. And as we go down a group, we increase the atomic radius. So if we look amongst one period, fluorine would have a smaller atomic radius than lithium. Lithium would be larger. And if we look amongst this group, lithium would have a smaller atomic radius than, let's say, cesium. So that's the basic trend. But let's talk about why. So it decreases across the period. I'm referring to this as going from left to right. As you move from left to right across a period on the periodic table, you are increasing the number of protons found in the nucleus of that atom. The more protons you have in the nucleus, the greater the Coulombic attraction. So that's a greater pull from the nucleus on the electrons, which means that the electrons are going to be pulled closer. So you can maybe think of the nucleus as being a magnet. And as we move across a period, right, we're just making the magnet stronger. And the electrons are so small that it doesn't matter that we're also adding electrons. As long as we're not changing the number of orbitals, the electrons will be pulled in closer. As we go down a group, atomic radius increases, and this is because we have more electron shells. I'm okay if you use the word shell. Although the Bohr model isn't correct, I'm just using them as a visual. Each of the different circles around the nucleus would be an electron shell. We think of it as like different energy levels at which electrons are found. So as you go down a group, we continue to add shells of electrons that surround the nucleus. And if you are adding these orbitals on top of each other, you're just going to continue to make the atomic radius larger and larger. So let's go through some examples together, and then I'll have you try some on your own. So for each of these pairs of elements, we want to know which one has the largest atomic radius? So we're first off starting with lithium and carbon. So I always start by finding them on the periodic table. We have lithium here and we have carbon over here. They're in the same period. And when two elements are in the same period, you compare the number of protons in their nucleus. Two elements in the same period are not going to have a different number of electron shells. They're going to have the same number of electron shells. The only difference is going to be the number of protons in their nucleus. Lithium has 3 protons, carbon has 6. A nucleus with 6 protons is going to pull electrons closer to it than an atom that only has 3 protons. So therefore, lithium is going to have the larger atomic radius. If we compare magnesium and barium, magnesium is right here, number 12, and barium is number 56. These elements are in the same group, and when two elements are in the same group, they differ in the number of electron shells. As you go down the group, the atoms have more and more electron shells, making them larger in size. So because barium is lower in the group than magnesium, barium will have the larger atomic radius. The next one, we're comparing chlorine and tin. So chlorine is over here, number 17. Tin is here, number 50. Here we have two elements that are not in the same period and not in the same group. However, because tin is lower than chlorine, we know that tin has more electron shells than chlorine. And when we have elements that are not in the same period, that is the number one thing we look at. That's the only thing we need to look at, is whichever one is lower has more electron shells and will therefore be larger. So don't overthink this. Just because tin is lower in the periodic table means it has more electron shells, so therefore it has the greater or the larger atomic radius. We do not need to compare anything else. I want you to pause the video here and with your periodic table, figure out which element in each pair has the larger atomic radius, and I want you to practice explaining why. When you're done, hit play. I'll show you the answers, I'll discuss the explanations, and we'll move on to the next trend. So hit pause now. Here are the answers to those 3 pairings. So looking at cesium and sodium, they're both in group 1. So we are comparing the number of electron shells that each atom has. Because cesium is lower in the group, it has more electron shells, which makes the atomic radius larger. Comparing aluminum and sulfur, they are both in the same period, so we are comparing the number of protons. Sulfur has 16 protons, aluminum has 13. So because sulfur has more protons, it has greater Coulombic attraction, which means that its electrons are pulled in closer than those of aluminum, making aluminum larger. Comparing calcium and iodine, we see that they're not even close to each other. However, because iodine is 1 period lower than calcium, that means that it has 1 more electron shell than calcium does, therefore making it larger in size. It does not matter that iodine has over double the number of protons in its nucleus, because electron shells trump that. Electron shells is just adding more and more volume despite how many protons are in the nucleus. I hope that makes sense. The next trend we're going to talk about is called ionization energy. This is referring to the amount of energy required to remove an electron from an atom. Typically, we look at the amount of energy required to remove a valence electron. When you put energy into an atom, we kind of did this in the flame test lab. If you put enough energy in, you are able to not just excite the electron like we did in the flame test, but we can actually eject it off of the atom, and that would be ionization energy. The basic trend is when you move from left to right across a period, you are going to increase the ionization energy. So that means that you are increasing the amount of energy required to remove an electron. And as you move from top to bottom in a group, you are going to decrease the amount of energy required to remove an electron. So you would decrease the ionization energy. So looking over here, the top right corner would have the elements that have the highest ionization energy, and elements in the bottom left corner would have the lowest. Let's look at the reasoning behind these trends. So we increase across a period from left to right for the same reason that we talked about with atomic radius. As you move from left to right across a period, there are more protons in the nucleus, which leads to greater Coulombic attraction. We're increasing basically the magnet that's in the nucleus, which means that the electrons are pulled or attracted, more attracted to that nucleus, which means that it's going to require more energy to remove the electron. I typically make the weird metaphor of like, the closer your children are to you, the less likely they are to be taken if you're in a busy place, right? Versus looking over here at fluorine, if your children are really close to you in a busy place, they're less likely to get lost, let's say. As we move down a group, we decrease the amount of energy required to remove an electron, so it basically gets easier for us to remove one because it's the same reasoning. As you move down a group, you increase the number of electron shells, which means that there's more electron shielding and less Coulombic attraction. So the electrons on the outermost part of an atom of potassium are less attracted to the nucleus than the outermost electrons on, let's say, sodium. Because these electrons aren't as attracted to the nucleus, it requires less energy to remove one, which decreases the ionization energy. So let's look at some example problems together. We want to know which element in each pair has the higher ionization energy, so which one requires more energy to remove an electron. The first one, we're looking at tin, which is number 50, and iodine, which is number 53. These are in the same period, so we compare the number of protons in the nucleus. Iodine has more protons in the nucleus, which increases the Coulombic attraction, which means the electrons are more attracted to the nucleus, and therefore it's going to require more energy to remove one. So iodine would have the larger ionization energy. Looking at nitrogen versus arsenic, both are in group 15. When we have elements in the same group, we look at the electron shells. So because arsenic is lower in the periodic table, it has more electron shells than nitrogen does, which means that the electrons on the outermost part of an arsenic atom are not as attracted to the nucleus as the outermost electrons in nitrogen, which means that it's going to be easier to remove an electron from arsenic. So that would be the lower ionization energy. So therefore, nitrogen would have the higher one because it has fewer electron shells. So therefore, it would require more energy to remove an electron. There's greater Coulombic attraction, less electron shielding. Looking at boron and oxygen, these are again in the same period, so we compare number of protons. Oxygen has more protons than boron does, which would lead to greater Coulombic attraction. The electrons are more attracted to the nucleus of oxygen than boron's electrons are attracted to its nucleus. So therefore, oxygen would require more energy to remove an electron, which means it has the higher ionization energy. Let's do the same thing where you pause the video, figure out which element has the higher ionization energy, work on explaining why, and then come back and hit play when you're done. Here are the answers for each pairing. Looking at potassium and francium, those are both elements in group 1. Potassium has fewer electron shells than francium, meaning there is greater Coulombic attraction, which means that it's going to require more energy to remove an electron off of potassium. Carbon versus nitrogen, they're both in the same period. Nitrogen has more protons than carbon, which increases the Coulombic attraction, which increases the amount of energy required to remove an electron. So that's a higher ionization energy. Aluminum versus iodine. Iodine has more electron shells than aluminum, so therefore aluminum has greater Coulombic attraction over its electrons, which means it's going to require more energy to remove one, which gives it the higher ionization energy. The last trend we're going to go over is electronegativity, which is how strongly atoms attract electrons. And I want you to add, in all caps, in a bond. It's super important that we know that electronegativity has to do with bonded atoms and how strongly each atom that's bonded together attract electrons that are being shared between them. So it's how strongly atoms attract electrons, in all caps, in a bond. The electronegativity trend is identical to the ionization trend, ionization energy trend. As we go from left to right across the period, we increase the electronegativity. And as we go down a group, we decrease electronegativity. Shocker, the reasoning why is identical as well. So as we go across a period, electronegativity increases because we have an increase in protons, which means we have greater Coulombic attraction. So electrons are pulled closer to the nucleus, which will include any electrons that are being used to bond. So electronegativity increases across a period because we have more protons. It also decreases down a group for the same reasons that we've said before. As we move down a group, we have more electron shells, which leads to more electron shielding, which means that there is less Coulombic attraction on valence electrons, and valence electrons are the ones that we use to bond. So if we form a bond way out here with potassium, any electrons out here are not as strongly attracted to the nucleus as, let's say, if we bond some electrons here on lithium. So therefore, lithium has a greater or higher electronegativity because those bonded electrons are more attracted to its nucleus than potassium, whose bonded electrons way out here would not be as attracted to potassium's nucleus. Let's go through another set of pairings. We want to know which one has the higher electronegativity. So looking at boron and oxygen, these are both in the same period. So we're comparing protons. Oxygen has more protons than boron, which means that it has greater Coulombic attraction, which means that it's going to have the higher electronegativity. Any bonded electrons are going to be more attracted to oxygen's nucleus than boron's. Looking at calcium versus radium, both in group 2, radium has more electron shells than calcium. And because it has more electron shells, its Coulombic attraction is lower, which means that any bonded electrons on the outermost shell in those outermost orbitals are not as attracted to radium's nucleus as they would be for calcium. So therefore, calcium has the higher electronegativity. Comparing fluorine and lead, we look at the number of electron shells. Lead has way more electron shells than fluorine, so therefore fluorine has a greater Coulombic attraction, which means it's going to have the higher electronegativity. So pause the video again, try these on your own, really focus on trying to explain why, and then hit play when you're done. So these are the answers you should have gotten. Looking at strontium versus beryllium, both are in group 2. Beryllium has fewer electron shells than strontium, so therefore beryllium's Coulombic attraction is higher, which means it's more likely to attract bonded electrons than strontium. Silicon versus chlorine are both in period 3. Chlorine has more protons in its nucleus than silicon, so bonded electrons will be more attracted to its nucleus than silicon. So chlorine has a greater Coulombic attraction, so therefore higher electronegativity. Rubidium versus bromine. Rubidium is one period down from bromine, so therefore it has one more electron shell. Because rubidium has an extra electron shell, there's more electron shielding. Therefore, it has a lower Coulombic attraction, which means that bonded electrons would not be as attracted to its nucleus than bromine. So therefore, bromine has the higher electronegativity. Hopefully this made sense. But that's it for periodic trends.